So, what are lipids? Well, lipids are biomolecules that contain fatty acids or steroid nucleuses. So, if you recall from the very beginning of the semester, I mentioned that there were three biomolecules that we were going to go over the semester. They were the sugars, the lipids, and the amino acids slash proteins, right? And so this is the lipids we're talking about today. And the lipids have fatty acids and steroid nucleuses. What is a fatty acid? A fatty acid is basically a carboxylic acid, like you learned from the last lecture, right there, and it is it is attached to a long chain carbon, right? Generally, these carbon chains are about 14 to 24, and they're even numbered because they get synthesized that way. Even numbered carbon chains, right? And at physiological pH, this carboxylic acid is usually in the carboxylate form, so O minus, like so, right? Not with an H on it. So lipids such as waxes, fats, oils, and phospholipids are esters that can be hydrolyzed to give fatty acids and other molecules, right? So we'll learn later on in the lecture more specifically about how lipids are naturally occurring and they're attached to things like glycerols and such. And then they get hydrolyzed into what you see here, the individual fatty acid, right? And then steroids, which are these, right here, are usually four fused carbon rings, and they can't be hydrolyzed, right? And they don't contain fatty acids. But things to note that are important is that they are soluble. Lipids are soluble in organic solvents, but not in water. And if you didn't already know, the word lipose actually means fat in Greek. And then they're also very prevalent in things like cell membranes, fat-soluble vitamins, and steroid hormones. So, again, we'll talk about steroids a little bit more later in the lecture, but let's talk about the fatty acids first. They come in four categories that we'll talk about in this lecture: the waxes, the triacylglycerols, which is most of the fats that are what you consume, right, and they're stored in your body. And then we have the glycerophospholipids, which are the cell membrane lipids, right? And then we have the sphingolipids. I've never been able to say that correctly in my entire career. Sphingolipids? I think that's how you say it. And you can see each one of these categories of lipids or fatty acids have a different structure. The waxes have a long chain alcohol with one fatty acid. Like I was saying before, the triacylglycerols, they have a glycerol attached to three fatty acids, right? And then the glycerophospholipids, which are part of the cell membranes, they have two fatty acids attached to a glycerol, a phosphate group, and an amino alcohol. And the sphingolipids are attached to, they have a backbone, a sphingosine backbone attached to a fatty acid, a phosphate group, and an amino alcohol. And so we'll talk a lot more about those in detail later on in this lecture. Continuing on, just a quick little side note about lipids and stuff and lipoproteins. So, in clinical lipid specialists actually work with patients who have lipid disorders, right? And lipid disorders are things that you've heard of before. High cholesterol. I think I have some high cholesterol. High triglycerides, which are the fatty molecules before they become fatty acids when you consume them, right? And according to heart disease and obesity, right? Well, so at a lipid clinic, what do? They do testing. They review the lipid profile of patients, and that includes the total cholesterol, the HDL, and LDL, right? And if you didn't already know this, HDL is actually good for you. LDL is bad for you, right? So here are the four phases of an artery being narrowed, right? And HDL, which is high density lipoprotein, it flows straight through your blood vessels, right? Just straight through, and you're doing fine with the HDL. The problem though is that we have the bad stuff, which is LDL, low density lipoprotein, which we'll talk more about specifically what each one of those are later in the lecture. They flow through your blood vessels too, right, before they actually get stored as triglycerides, in your adipose tissue. But the problem though is that they get attracted to the sides of the walls of your arteries, and so they start bunching up on your arteries. And the more they bunch up, the more they get narrow, right? And so that's what causes clogged arteries, and eventually a heart attack if it's in your heart or something like that, right? The thing about it is though that HDLs, since they're they flow through your arteries so well, and if you consume a lot of HDLs and your HDLs are high, they can actually help reduce the LDLs in your body, right? So usually when you take a test for your lipid panel, right, HDLs are always supposed to be high, or you need them to be high. It's good to have them high. And your LDLs are supposed to be low to prevent clogged arteries, right? So just a side note before we jump into the real chemistry of the matter. All right, so let's talk about fatty acids specifically, right? Like I said before, on the very first intro page, they're long-chain, unbranched carbons, right, with a carboxylic acid, all right? And like I was saying before as well, generally at physiological pH, the carboxylic acid is actually in the form of its conjugate base, right? The carboxylate version. Okay. They're insoluble in water because of the long carbon chain. It makes them very nonpolar, right, on this big end, right? So it makes it very nonpolar and not water soluble. But this end is actually very polar, right, as we already know, because that's a carbonyl, isn't it, right? There are a couple different types of fatty acids. There's the saturated fatty acids that don't contain any carbon-carbon double bonds. And then they're the unsaturated fatty acids that contain carbon-carbon double bonds, right? So just a little note on how to draw fatty acids. It's just like drawing every other carbon-based molecule, right? You have the ball and stick there of lauric acid, and then you have the condensed structural formula there of lauric acid. But most commonly, since these things are so long, we will draw these fatty acids like this, the line angle formula, right? Where each point of the line, like peak and valley of the line angle, right, is a carbon. And if there's nothing else there, and carbon is supposed to have 4 bonds to something, then 2 of those have to go to hydrogens, right? And you just don't draw them out like you do up here, just to save time. So there's a carbon there, 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 there. And generally, when we count the carbons to name these things, carbon number 1 starts on this end. That's a terrible arrow I just drew. There we go. Carbon number one starts from this end, right? And then the last carbon starts on this end, right? Because we always start where the functional group is attached, right? So we'll learn a little bit about omega-3 fatty acids later on, right? In fact, they're not omega-3 fatty acids, they're omega-3 fatty acids because they're 3 carbons away from the end with the omega carbon, right? Where the double bond is located, which we'll see in a second. I'm sorry, I'm jumping ahead. I do that a lot. I apologize. Let's keep going. Boy, do I like my fatty acids, right? So let's take a look at some common fatty acids that are saturated, right? Again, saturated fatty acids are the ones that only have single bonds, carbon-carbon single bonds, right? So that's lauric acid. Lauric acid has 12 carbons in it. It's present in coconut, right? So I was making something yesterday, or maybe it was the day before, and I had to use a lot of coconut milk. That's some fatty stuff right there. Melting point is 44 degrees, which makes sense why it melted in the pot when I was cooking it. And that's its structure right there, right? 12 carbons long and completely saturated. That means there's a hydrogen present at every single bond that's not bonded to a carbon, right? That's fully saturated. Another one, myristic acid, 14 carbons. That's present in nutmeg, has a melting point of 55, and there's its structure right here, right? Again, line angle structure. Very, very common is palmitic acid. Palmitic acid is actually made by your body, 16 carbons long. I think I mentioned palmitic acid once in a lecture before. Fatty acid synthase makes it. That's a whole thing that you'll be learning about later on in the class, later on the semester, which is kind of funny because the semester's almost over, but you're still going to learn about it. That's in palm oil, and present there, but it's also present in your body because your fatty acid synthase makes it. It's got a melting point of 63 degrees. And then there's stearic acid, the last saturated fat that we have here, 18 carbons long. It's an animal fat, right? And it has got a boiling point of 69 degrees. So what's the point of this, right? Well, the point of this is that as more carbons get added, right, the higher the melting point is, right? Which means it's solid at room temperature, okay? These are all in Celsius, and room temperature is 25 degrees Celsius, and all these are solid at room temperature, and they get more and more solid and don't melt at higher temperatures as the carbons increase, right? As the carbons increase. So we'll elaborate on that a little bit later. All right. So next, we've got our monounsaturated fats. What does monounsaturated mean? Mono means one. Unsaturated means missing a hydrogen, right? Or a couple hydrogens. And yes, one double bond in the carbon chain, right? So one of the most common is palmitoleic acid. Palmitoleic acid. And it has 16 carbons, and I didn't mention this in the last slide because there were 0 there, but since this one has a double bond, the number after the colon is always the number of double bonds, right? So 16 carbons with one double bond, present in butter, right? Its melting point is 0, right? And so it's pretty much like liquid at room temperature, and its double bond is right there, right? So when an unsaturated fat is unsaturated, or sorry, let me say that one more time. When a fat is unsaturated, right, that means it has a double bond in it, one or more. And in this case, with palmitoleic acid, that double bond is 1, 2, 3, 4, 5, 6, 7. 7 bonds away from the omega carbon, right? And when you draw a double bond there, that means that these carbons here actually both lose a hydrogen, right? So there's 2 hydrogens missing here, right? Okay, so we got oleic acid, right? Oleic acid. It's got 18 carbons with a single double bond. It's most common in things like olives, so like olive oil. Melting point is 14 degrees. So it is also liquid at room temperature, right? And there's its double bond there, right? And of course, again, if the double bond wasn't there, then there would be hydrogens up here and up here, right? Up here and up here. But since there's a double bond there, those hydrogens are gone, which makes it unsaturated. A single double bond means monounsaturated fat. Next is the polyunsaturated fats. And we have the first one here, linoleic. Oh, there we go. Linoleic acid. And it's got 18 carbons with 2 double bonds, right? Seen in soybean, safflower, and sunflower oils. Its melting point is -5 degrees, mother. Then it's definitely like liquid at room temperature. And you can see here that it has 2 double bonds, right? Making it polyunsaturated. Polyunsaturated just means you've got more than one double bond, right? There's also linoleic acid. Sorry, this is hard to say. Linolenic acid, right? Okay, there. Let's not get this confused. The first one is linoleic acid, and then the second one here is linolenic acid, right? There's only a difference of one letter, the end. I even just got confused there because it looks so similar, right? And the difference between those two, right, even though they're both 18 carbons long with 2 double bonds, right, is number one, this comes from corn flour. It's got a melting point of negative 11 degrees, so liquid at room temperature. Corn flour. Did I say corn flour? Sorry. Comes from corn. Negative 11 degrees Celsius is a melting point, and its double bonds are there and there. Huh. That's a typo right there. That should be 3. Yeah, so that's a typo. That should say 18.3. Correct that in your notes. Because there's actually 3 double bonds. That's really weird. Yeah. 3 double bonds. Okay. Then we have arachidonic acid, another polyunsaturated fat. It's 20 carbons long with 4 double bonds, right? Its melting point is negative 50. And it's got double bonds at that point, that point, that point, and that point. So it's definitely also liquid at room temperature, right? Definitely liquid at room temperature. And it's got 4 double bonds there to show for it. Again, sorry about that typo there. That should actually say 18.3. So make sure you fix that in your notes. Okay, so let's talk about now cis and trans unsaturated fats. We'll use oleic acid as our example here, right? In the picture that was drawn in the previous slide, oleic acid was presented with a cis double bond right there at the 9th carbon, right? Turns out, though, you can also draw oleic acid as a trans double bond, okay? So the difference here, though, is that in the cis double bond, it puts a kink in the fatty acid, long fatty acid chain, right? Whereas when it's trans, it stays straight, like if it were, as if it were saturated, okay? But most naturally occurring unsaturated fatty acids will have 1 or more cis double bonds, right? And we'll talk a little bit more about trans double bonds and fatty acids a little bit later. All right. So, all this talk about fatty acids, it turns out that our body needs them, right? And so humans, we actually are capable of synthesizing some fatty acids from carbohydrates, right? Or other fatty acids, right? But we can't synthesize sufficient amounts of polyunsaturated fats, such as the linoleic acid. I keep on getting these like saying wrong. Linoleic acid, and then linolenic acid, and then the easier one to say is arachidonic acid. Right? So where do we get them? We have to eat them. We have to eat these polyunsaturated fats. And so whenever you have to consume something to get it, like a mineral or something like that, or an amino acid or a fat, and your body can't produce it itself naturally in abundant quantities enough for you to survive, we call those essential, right? Essential fatty acids, right? So here we have the structure of linoleic acid, then we have linolenic acid, right? And then we have linolenic acid, right? And we have arachidonic acid right here. And I'm glad to see that it's written correctly here, right? With 3 double bonds, right? So the difference between gamma linoleic acid, linolenic acid, and dihomo gamma linoleic acid, right, is that there are 2 extra carbons here than there are here. Okay? So the one we talked about before was this one in the previous slide. Remember that this is the number of carbons present, and this is the number of double bonds present. Right? Oh, and then this right here, which wasn't in the other notation, is the position of the first double bond from the omega end, right? So, for example, that's a 6. 1, 2, 3, 4, 5, 6 is where the the first double bond is, right? Again here, 6. 1, 2, 3, 4, 5, 6 is where the first double bond is. Make sense? I know it does, doesn't it? All right, so let's talk about some properties of these unsaturated fatty acids. And I said that before I changed the slide. There we go. The properties of these of some saturated fatty acids, right? Again, they contain a single. They contain only single carbon-carbon bonds, and when they do that, since they are these long chains, they can fit very close together in a very regular pattern, right? They have super strong dispersion forces between the long carbon chains, which means that they have higher melting points. So that means that they're usually solid at room temperature, right? Things like butter, for example, right? Butter. So we have stearic acid here. And stearic acid has a melting point of 69 degrees. It's kind of small on my screen, but I hope you can see it. 69 degrees. And notice it is a saturated fatty acid, right? No double bonds at all in the chain. But again, we're using oleic acid again as an example. And there is a kink double bond right there, right, for oleic acid. And so since it's got that kink there, the molecules of oleic acid can't fit together as closely, as tightly as the fatty acids, the fatty acids that are present in stearic acid, right? The carbon chains that are present in stearic acid. And since they don't fit as closely together, they have a much lower melting point, and that's why oleic acid is liquid at room temperature, and stearic acid is solid at room temperature, right? So remember that. And so what the drawings actually show here is what I just said. We have here very lined up stearic acids. You know, they fit together super well, right there, right? But since oleic acid here has that kink from the double bond, they just kind of all, you know, they sit together very disorderly, right? They don't fit together very well, and they no longer have those strong dispersion forces that will hold them together, so that they have so that they are solid at room temperature. They're liquid at room temperature, right? And then and I've already said all this stuff here too. Unsaturated fatty acids, cis double bonds cause a kink. I said that, giving molecules a regular shape and allowing fewer interactions between the molecules, right? And then the reduced interactions of the fatty acids with the cis bonds reduces the melting point of the molecules, right? So the more interaction, the closer they are to each other, the more interaction there can be between the molecules, and the more likely the higher the melting point. But if there's less interaction, then the lower the melting point, right? So let's do a really quick review about fatty acids. Again, we'll use oleic acid again as our example. Why is this molecule an acid? Well, it's an acid because it has this right here. Right? It has the carboxylic acid right there. And remember, at physiological pH, that carboxylic acid is normally in the carboxylate form. Right? It's lost its proton. Okay? It's lost its proton. How many carbons does oleic acid have? You can count them up, right? There's 1 there, plus 7, plus 1, plus 1, plus 7, plus 1, equals 18 carbons. Excuse me. Is this a saturated, monounsaturated, or polyunsaturated fatty acid? There's one double bond there, making it a monounsaturated. Is it likely to be a solid or liquid at room temperature? Well, we just saw on the last slide, right, that it's got this double bond right there in the middle of it, making that kink, so that it can't be very close to each other, so that there's more interaction between those molecules, right? And since there's not a lot of interaction between the molecules because they fit together so irregularly, um, they're not liquid. I mean, sorry, they're not solid at room temperature. They're actually liquid at room temperature. And would it be soluble in water? Well, that's pretty self-explanatory because many I can't think of any fat that's actually soluble in water, like soluble, but this one definitely isn't. Not soluble in water, right? Excuse me. Let's keep on trucking along here. Ooh. This is going to be fun right here. Prostaglandins, right? Why do you feel pain? Well, it's all because of prostaglandins, okay? Excuse me. So what are prostaglandins? They're hormone-like substances that are produced in cells, right? They're also known as eicosanoids, and they're formed from arachidonic acid, the polyunsaturated fat of carbons that we spoke of earlier, right? One of those essential fatty acids, right? It only differs by the substituents that are attached at the 5-carbon ring, right? That's the only difference it is, right? So, did I say that clearly? I didn't say that clearly. It differs from arachidonic acid by the substituents attached to the 5-carbon ring, right? So here's your arachidonic acid, and here's your prostaglandin, right? So prostaglandins have many functions, such as lowering and raising blood pressure, and stimulating contraction and relaxation of smooth muscles of the uterus. I didn't actually know that. That's interesting. But when tissues are injured, arachidonic acid, right, is converted to a prostaglandin. And that is what produces inflammation and pain in the area, right? And so you have a picture here of this guy who smashes his finger using a hammer. And so when that happened, all his arachidonic acid, right, started being converted into prostaglandins, right? And that's why he feels pain, inflammation, and fever. And you can actually stop that, actually, or you can mitigate it a little bit by using NSAIDs or non-steroidal anti-inflammatory drugs, right? And those are things like aspirin or naproxen, things like that. They'll block the process of arachidonic acid being turned into prostaglandins. I actually had a personal experience with that this weekend. It's kind of sad, actually, because my dog, we were training him, and he got very upset for some reason, and he bit me on my hand right there. See? And let me just tell you, there were a lot of prostaglandins being produced from me being bit. It hurt a lot, right? It bit me in my leg, too. And actually, interestingly enough, I went to get it checked out at the urgent care, and it hurt more when they were putting in the lidocaine to numb the area so they could put stitches in than when I was being bitten by my dog. Yeah, so maybe it was better not to even go to the urgent care. Who knows? Because now I have to get these stitches out and it's another pain. Sorry, off topic. Well, it's not off topic because we're talking about prostaglandins, right? And prostaglandins are what cause pain, and they come from arachidonic acid. Remember that. That's important. Okay? That is important. So, in the same vein as prostaglandins, we'll talk about the things that can stop the production of prostaglandins, and those are the NSAIDs, the non-steroidal anti-inflammatory drugs, things like aspirin, ibuprofen, that's Advil and Motrin, or naproxen, that's Aleve or naproxen, right? My personal favorite is naproxen. I always have at least, a few months supply of prescription strength naproxen in my medicine cabinet. And it definitely helps relieve the pain, blocks those arachidonic acids from becoming prostaglandins, right? So it makes you think, if it's all about pain, maybe I should just stop producing, or maybe I should stop consuming, because it's an essential fatty acid, so you have to eat it to actually have it in your body, right? But if it's only there to signal you for pain, and you don't like pain, maybe we should stop eating that, right? Is that even possible, to stop eating arachidonic acid? I don't know. Anyway, that was interesting. Oh, here we go. Everybody, let's talk about this. Let's talk about the omega-3 fatty acids, right? The omega-3 fatty acids. So, fish oils have omega-3 fatty acids. Those are the unsaturated fats that I was talking about before that have the double bond begin at the third carbon from the end, right? Because the first carbon over here is the alpha carbon. So the last carbon in the chain is known as the omega carbon. Oh my god, that's a terrible... My Greek teacher would kill me. But that's supposed to be an omega symbol, right? And so everybody, like in the media and in the news and like, you know, like even at GNC, they always call them omega-3 fatty acids, but in fact it doesn't mean omega-3. That actually means omega minus 3. And what that actually means, like I was saying before, is that, for example, in linoleic acid, right, or ALA, right, the double bond begins at the third carbon from the omega end of the molecule, right? So it's omega, right? Let me try to draw this omega again, and maybe I won't be embarrassed. Does that look like it? That doesn't even look like omega. Anyway, omega, right, minus 1 carbon, 2 carbons, 3 carbons, right? And that's why it's called omega minus 3 fatty acids. It is not omega-3 fatty acids, it's actually omega minus 3 fatty acids. So, other omega-3 fatty acids, eicosapentaenoic acid. Wow, I can say eicosapentaenoic acid with no problem at all. But for some reason, linoleic acid is a problem for me. Anyway, it also has a carbon there at the third carbon, right, from the end, the omega minus 3 carbon. And then we have docasa. Yeah, that's right. Sorry, docosahexaenoic acid, DHA, right? And it also has a double bond beginning there at the omega minus 1, 2, 3 carbon, right? And those are all omega minus 3 fatty acids, right? Not omega 3 fatty acids, omega minus 3 fatty acids. In fact, I challenge you to go to GNC, right? Or somewhere, maybe a pharmacy. Well, the pharmacist would know. But I challenge you to go to GNC and see when you're going to get your fish oil pills, right? Whether or not your associate there calls it omega minus 3 fatty acids, or he or she calls it omega-3 fatty acids. And if they call it omega-3 fatty acids and not omega minus 3 fatty acids, you can call them out on it. I used to do that. That's bad. I shouldn't do that. Very bad. Very similar, of course, to the omega-6 minus 6 fatty acids, right? The omega minus 6 fatty acids, which we're already talking about before, because arachidonic acid here is causing me all my pain, right, from being bitten by my dog. But again, right, these are the omega-6. GNC guys got me saying it wrong. The omega minus 6 fatty acids, of course, begin their double bonds at the 6th carbon from the end. 1, 2, 3, 4, 5, 6th carbon, right? And everybody knows fish has high levels of omega minus 3 fatty acids, right? Everybody knows that. But I actually don't like fish. So we can actually get it from other things too, like flaxseed. I even think for some reason I feel like fish pills, like fish oil pills, smell like fish, so it kind of makes me like, you know, not want to take those either. So I might just stick with the plant versions of omega-3 fatty acids. Right. More about omega minus 3 fatty acids, right? Well, so when you have arteriosclerosis or in heart disease, cholesterol actually forms plaque and adheres to the walls of your blood vessels, right? The blood pressure rises and it has to squeeze the blood through a smaller opening in the blood vessel. That's not good. Not good stuff, right? Not good stuff. More plaque forms, and then there's possibilities of heart attack and blood clots. Not good, right? But omega minus 3 fatty acids, they're like magic. They tend to lower the tendency of platelets to stick to each other, right? Reducing the possibility of blood clots. right? That's pretty neat. So cold water fish here. I had to put a picture of a fish in there, and they're a source of omega-3 fatty acids, right? But look here in this cool little chart we have here: walnuts, flaxseed oil. Oh, I love soybeans and canola oil, and I love cooking with canola oil, right? You can get omega-3 fatty acids from there. The alpha linoleic, I can't say it, linolenic acid, right? You can get that from there, but everything else has to come from fish, right? You can get the omega-6 fatty acids from corn, safflower, soybean, cottonseed, and sunflower oils, right? And meat, poultry, and eggs too. So I really do like meat and poultry and eggs. At least I'm getting enough of my omega-6 fatty acids, right? And there's also even omega-9 fatty acids, which we talked about earlier too, and that's in olive oil. So really, the unsaturated fatty acids are really good for you, right? They're really good for you. You should have a lot of that in your diet, right? Now let's talk about the different categories of fatty acids, right? The first one we'll talk about are the waxes. Waxes are esters of saturated fatty acid chains and long chain alcohols, each containing from 14 to 30 carbon atoms long, right? So here's your fatty acid part right here, right? And then here's the carboxylic acid part, right? Quote unquote. But it's really not a carboxylic acid, it's an ester. Why is it an ester? Because the other side is not connected to an H, it's connected to a long-chained alcohol, right? It's connected to a long-chained alcohol. So that's the difference between a regular fatty acid, right, and a wax, right? Mostly we see waxes in the coatings of leaves, right, and it prevents them from drying out, right? It prevents them from drying out. But let's talk about some different waxes, right? Here's beeswax. Isn't that where honey comes from, right? Source honeycomb, obviously, right? And this is a very, very big molecule. Look at this, right? There's 15 carbons on that side, right, of the ester, and then this side of the ester, there's 30 carbons. That's a pretty big molecule, right? Pretty big molecule. So we have that in candles, shoe polish, wax paper, right? I'm not sure what Carnauba wax is. I've never heard of that before. But that's even bigger. 24 on that side. The Brazilian palm tree, right? Waxes for furniture, cars, floors, and shoes. That's interesting, right? And jojoba wax. Not as big, right? Comes from the jojoba bush, which I've never even heard of before. But that's in candles, soaps, and cosmetics. Interesting stuff. Learned so much stuff, like so much practical stuff in this class, right? Me, because since I'm a chemist, I was trained as a formal chemist. We never really get this into the practical. Oh, this is what's sitting on your shelf type of chemistry, right? In your bathroom sink or something, or in your bathroom vanity and stuff. So it's kind of interesting. Anyway, so the next category of fatty acids are the triacylglycerols, which I'm super familiar with because these are the ones that are in animal fats, and this is how the fats that are stored in your body are stored. This is what happens during fatty acid synthesis, in metabolism, and then when it breaks down and goes into your let me rephrase. When you consume these triacylglycerols and they get broken down into their substituent fatty acids and then get transported to your adipose tissue, right? That's all this stuff. So let me just say all that again, except in a more organized fashion, right? The triacylglycerols, these are the fatty acids, right, that are stored in body fat, right? So I was actually taught when I was in chemistry that they were called triglycerides, right? Triglycerides, and we call them also triacylglycerols too, because the reason why is because they're being held together. 3 fatty acids are being held together with a glycerol, right? So that's why it's a triacylglycerol. So you'll hear me use triglycerides and triacylglycerols probably synonymously, right? Like interchangeably. Is that right? Yeah, that's right. Interchangeably. But for the purpose of this class, use the word triacylglycerol. Okay. And then using stearic acid as the example here, we make a triacylglycerol by combining glycerol with 3 molecules of stearic acid. And then that makes a triacylglycerol known as glyceryl tristearate, right? Or for short, tristearin. Okay? And you also get 3 waters out of the reaction as well, right? Again, the glycerol is attached to the fatty acid with an ester bond, right? Remember, this used to be right here, just an H there, right? Or an O minus, right? An OH or an O minus, right? So this reaction actually occurs pretty commonly in your body. When you, for example, consume bacon, you know that and there's fat in bacon. When you consume it, it's actually in the form of the triacylglycerol, right? Which is this guy right here. Because animals, including yourself, store their fat like that. But that big molecule can't be transported through your cell membranes. It can't be transported through the bloodstream to get to your adipose tissue to be stored, right? And it's not easily broken down into sources of energy, right? And so when you consume these triacylglycerols, for example, this one right here, right? It goes in your stomach, and your body has these enzymes called lipases, right? And these lipases actually break it down into their substituent fatty acids and glycerol, right? Their substituent fatty acids and glycerol. So stearic acids, individual stearic acids, just so that they can be transported, right? There's other processes too for the transportation itself, like that include things like cholesterol and your A1Cs and things like that. But while they're being transported through your body, they are in their individual fatty acids. But then once they get to your adipose tissue, right, like your butt or your stomach or something like that, they're converted back into the triacylglycerol form, and that's how your body stores fatty acids, right? That's how your body stores fatty acids. There are also these things called mixed triacylglycerols, where you can have like 3 different fatty acids attached, like a stearic acid, an oleic acid, and a palmitic acid. That's called a triacylglycerol, right? But yes, triacylglycerols, also known as triglycerides, they're exactly what you think they are. They're the thing that you get from your lipid panel, and your doctor is telling you, hey, you need to cut out the fat, right? Or you need to exercise more. When you're saying your triglycerides are too high, they're the same thing. Because the triglycerides are the form of fat before it gets stored in your body, right? Sorry, let me say that again. The triglycerides are the form of fat that you consume, right? They get broken down into their substituent fatty acids, and then they get turned into triglycerides again to get stored in your body, in your adipose tissue. So on that same vein, in that same note right there, right, we have a super cute little polar bear cub right there. So adorable. Just laying on top of his mom that's hibernating, right? And the reason why this polar bear is hibernating and can survive while it's hibernating is because it ate a lot of food, right? And it stored all the fats from that food in the form of triacylglycerols, right? In the form of triacylglycerols. And so while that mama bear is sleeping, hibernating, she's losing weight because the only source of energy she's getting, food she's getting, right, sustenance, is from the triacylglycerols that she's consumed from large quantities of plants, seeds, nuts, that are really high in calories, right? Interesting stuff. Interesting stuff. That so does that mean then to lose weight, all you have to do is eat a whole bunch of triacylglycerols, like high calorie plants, seeds, and nuts, and other high calorie things, and then just take a long nap? I don't know. I wonder why it works with bears and it won't work with people. I'm thinking about that too much. All right, let's keep going. Let's keep going. Having trouble turning the page here. There we go. Oh, exciting stuff. Let's do some triacylglycerol drawing practice. Okay. We want to draw a triacylglycerol containing 3 molecules of myristic acid. That means, wow, there's whoever wrote this question, me, right? Made this super easy for you guys because it's 14 carbons long and it's got 0 double bonds, right? So, yeah, I guess you're not gonna have to memorize any like actual fatty acid names for this question, right? Anyway, so let's start it out. Let's draw the triacylglycerol version here, right? So when I do this, I usually always start out with the glycerol part, right? CH2, CH2, right? And then the glycerol part. Okay, that's the glycerol part. By the way, if it was just glycerol and we weren't drawing the fatty acid part of it, right, there would be an H at the end of the glycerols, and that would there would be H's here, right? So this is glycerol by itself, just so you know. Right, that's glycerol. Okay. But since we're drawing the triacylglycerol version of glycerol, right? There are no H's there, or there. Why are there no H's there? Because now we have to draw the fatty acid that goes with it. The next thing I always draw is the carbonyl part, right? And then 14 carbons long. You have a choice here. You can do it the easy way, which I will do it the easy way here. You can do one bond up, like that, and then put parentheses CH, right? And then, sorry, it was supposed to be 2 and I actually drew it a 1 there, so I'm trying to fix that there. Put CH2 because there's going to be a bunch of methyls, right? Or CH2s. And to be exact, there will be 12 plus one more methyl group, right? And now, sorry, excuse me. Now we know. Now we see 14 carbons, 1 there, 12 here, and 1 there, makes 14 carbons, right? And do that for the rest of them. Whoops. CH2, there we go. 12 CH3. And that is your myristic acid version of the triacylglycerol. Okay? Triacylglycerol. Let's do this the other way. Let's do this with a line angle instead. Okay? Line angle. So again, we'll do the glycerol first. Right? The glycerol first. And then we'll do the carbonyls next. Right? And then we'll draw the carbons. So we already have 1 carbon here, 2 carbons there, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's a line angle version, right? Let's do it again. 1 carbon there. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Alright? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I hope I counted those right. I'm Asian, so it's hard. Math is hard for me. So, yeah. Make sure I counted that right. I'm pretty sure that's right, though. But that's how you draw it. Oh, man. More about... This is a little bit all over the place today. No, I'm just kidding. More about melting points of fats and oils, though, right? Just like, I guess this is my little review, my little summary of melting points. A fat is usually solid at room temperature, right? And an oil is usually liquid at room temperature, right? Oils usually come from plant sources like palm oil, coconut oil, right? Whereas fats come from meats, whole milk, butter, and cheese, okay? So olive oil and peanut oil are monounsaturated fats, and they contain a large amount of oleic acid, right? And remember, oleic acid is actually liquid at room temperature, right? Corn, cottonseed, safflower seed, sunflower seeds have polyunsaturated fats because they contain large amounts of fatty acids that have two or more double bonds, right? Palm and coconut oils are solid at room temperature because they mostly consist of saturated fats, right? So basically what we were saying before, saturated fats, solid at room temperature. Unsaturated fats, liquid at room temperature, right? And this little chart here, the yellow is the polyunsaturated fat, the orange is the monounsaturated fat, and then the blue is the saturated fat, right? And it actually shows you these concentrations of each, like the proportions. So, for example, in beef tallow, which is just beef fat, rendered beef fat, right? So, like whenever you smoke a brisket, I do a lot of smoking of like barbecue at home, and when you ever smoke a brisket, all this fat like starts to render, like it drips off the meat and stuff. But you really want to put that back onto the meat so it stays moist. But it drips down, and all this liquid fat comes down when you're smoking the meat, and then you can collect all that, and it's like a yellow liquid, and then when it's warm, but when it like gets to room temperature, it actually solidifies because it's animal fat, right? Beef fat, for example, and you can see here that the proportion of polyunsaturated fat to monounsaturated fat and saturated fat and beef tallow, right, is like 1-to-1 to like almost nothing. So that's why beef tallow is pretty much solid at room temperature, right? Same thing with butter. Butter is almost all saturated fat. That's why it's solid at room temperature. You can actually add other polyunsaturated fats and monounsaturated fats to butter, like oils and stuff, to make it more soft so that you can spread it on your bread, right? So butter spread's not real butter, right? Oh my God, I used to think that country crock butter was real butter, but it's not, right? It's actually just a mixture of oils so that it's softer, so you can actually spread it on bread, right? So get yourself real butter if you want real butter. Don't use that country crock spread stuff, right? Coconuts, mostly saturated fat, which makes sense because when you got a can of coconut milk or juice, it's like literally a solid chunk until you melt it down, right? But then you look here at the liquid oils here, and olive, canola oil, right? Both have overwhelming amounts of monounsaturated fats, right? And then soybean oil, sunflower oil, safflower oil, and corn oil, all overwhelming amounts of polyunsaturated fat, except for corn oil has a lot of monounsaturated fat, right? So that's why those guys are all liquid at room temperature, right? And we're going over this a lot because you might have questions on an exam, on a quiz, or something that's like, is this going to be is this saturated fat going to be solid at room temperature? Is this unsaturated fat going to be liquid at room temperature? Blah 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 blah, that kind of thing. So it's probably why I'm talking about it so much. All right. Oh, here we go. Finally, to some reactions, right? So there's a reaction we can do called the hydrogenation reaction, right? And what that does is that it takes a double bond between two carbons, right? And hydrogen gas with a nickel catalyst, right? And it turns that double bond into a single bond. So then What that means is that when you used to have an unsaturated fat here, right? Say a monounsaturated fat, we'll say a mono fat, right? A monounsaturated fat there, right? After you treat it with these conditions, you get a saturated fat. We'll call it a sat fat. Sat fat. Interesting. Very interesting. Okay, so you can do this, right, by bubbling hydrogen gas through heated oil, right, and like I said, in the presence of a nickel catalyst. So here we go. We have a glycerol trioleate, right, or triolen, right, triacylglycerol, right, and we can do this reaction with some hydrogen gas and some nickel, and we get glycerol tristearate or tristerin, right, which is a single bonded saturated fat. Okay, remember that. Remember what's happening here. Okay, we're turning a monosaturated fat into a saturated fat. Okay. So here's something interesting. In commercial hydrogenation, the addition of hydrogen is stopped before all of the double bonds in liquid vegetable oil becomes completely saturated. The partial hydrogenation of liquid vegetable oil changes it to a soft, semi-solid fat that is more saturated product and has a higher melting point. And that's what you're using to spread your butter, right? Literally, that's what country crock is. It's oil that's been partially hydrogenated, right? It's not real butter. I guess they're not lying when they say stuff like, I can't believe it's not butter. But I think real butter, is healthy for you. Kind of jumped the gun on that, didn't I? I mean, I had a whole little point about it here, but I talked about that on the previous slide. I mean, there's just some things that kind of get to me, and one of those things is having fake butter. Anyway. Okay, next. Hydrogenation continued with trans fatty acids. Remember we were talking about trans fatty acids before, right? We can have a cis fatty acid that is hydrogenated like we were talking about in the previous slide and make it become a saturated fat, right? With the nickel catalyst. Oh, I'm sorry. I didn't realize that was actually a middle part of the reaction. That wasn't a... Let me clear that and try that again. So we have our cis fatty acid here, right? And what happens is that in the presence of hydrogen gas and nickel, the nickel will actually position itself over here to stabilize these two carbons, right? And when it stabilizes those two carbons, and you add in the gas, the hydrogen gas, right? One of two things can happen. You can either get the undesired trans fatty acid, right? Because the nickel catalyst was unsuccessful, and instead of having your cis fatty acid like you had before, now you have a trans fatty acid, right? Or you can get your desired product, which is the saturated fatty acid, right? And notice here, you knew that the nickel catalyst was unsuccessful, and you got this undesired product here because the hydrogen gas, right, got knocked out here, right? It didn't go into the making the single bond out of the double bond in the desired product, right? So in your body, trans fatty acids actually behave like saturated fatty acids, right? And they're estimated to be 2 to 4% in total calories, of our total calories. But the problem with trans fatty acids, is that they raise the LDL cholesterol. Remember what I was talking about before with your LDL, low density lipoprotein, right? So those are the things that carry the fats from your diet into your bloodstream and then take them over into your adipose tissue for storage, right? But the problem is that they like to clump a lot in your blood vessels, and then you get clogged arteries and you can have a heart attack, right? And LDLs do that, okay? And what trans fatty acids do, trans fatty acids really like being in LDL, so it raises your LDL, right? That's bad. And so, since it raises your LDL, that means it lowers your HDLs, your high density lipoproteins, which are the ones that are actually supposed to flush out all the fats that are in your blood vessels, right, and take them over to the adipose tissue for storage, right? So that's why people say that eating trans fatty acids is so bad for you. You might as well just eat real butter, right? And so one of the things that I was always concerned with is that, like, the fake butter thing. Well, you get fake butter, like in Country Crock, for example, uh, by partial hydrogenation, right? But butter is already fully hydrogenated, right? Butter is already saturated. So why not just go with the naturally, saturated stuff anyway, when it's like better for you than the partially hydrogenated stuff, right? Because you don't have to go through this reaction here, right? You don't have to go through this reaction here to hydrogenate it and possibly get the undesired trans fatty acid, because trans fatty acids are bad for you. Trans fatty acids raise your LDLs and lower your HDLs, right? So if I'm gonna eat some fat, I'm gonna eat some real butter, kind of like Paula Deen, right? Puts like 2 sticks of butter in one meal. Again, not that much. That's pretty unhealthy. Anyway. Let's talk about some more trans fatty acids. I didn't know I had so many slides about this. I did, actually. So trans fatty acids, they're in food that naturally occurring trans fatty acids are included in milk, eggs, and beef, right? They also are in deep fried foods, baked goods, right? And crackers, chips, right? Soft margarines, right? That's what I was talking about with Country Crock, like margarines. They're hydrogenated, and vegetable shortening. So all these things here go through a hydrogenation process, right? And so they can result in some trans fatty acids. And and some people actually deep fry their food in things like shortening and stuff, right? Like Crisco. That's why you can get it in there too. Okay. More reactions of trans fatty acids. More reactions of triacylglycerols, right? So in the presence of a strong acid like HCl or sulfuric acid, or digestive enzymes called lipases, I already said that before, jumping the gun again, right? You can actually take your triacylglycerol, right, and add water to this bond here, right, using the acids, right? By the way, your stomach has an acidic environment, and so in conjunction with that acidic environment, which is hydrochloric acid in your stomach, and the digestive enzymes called lipases in your stomach, right, and also later on in your small intestine as well, you can break down easily triacylglycerols into the substituent fatty acids to better absorb them. Okay, so that happens in this case because you can add water across these 3 single bonds here, breaking them apart, right? And when you break them apart, you get your glycerol again, like I was saying before, and your 3 palmitic acids, 16 carbons long, right? 3 palmitic acids. So that's the hydrolysis of fatty acids. Okay, hydrolysis of triacylglycerols. So just to review, just to make sure you remember, when you consume fatty acids, they're in the form of triacylglycerols. Then they enter your digestive tract, right? And after they enter your digestive tract, they encounter things like acid and digestive enzymes called lipases. And once they do that, they are hydrolyzed, broken down by water, right? Hydro means water, lysis means like cut, right? Or open up or something like that, right? And when they do that, they break the triacylglycerols that were the storage fats for the animals that you're eating into the substituent fatty acids. For example, here was 3 palmitic acids, and then it's glycerol, right? And then using those substituent fatty acids in their single chain forms, They are then transported through the body, through your alveoli, not alveoli, that's your lungs, sorry, your villi. There it is. My French biology just escaped me for a second. Your villi and your small intestine, they're transported through the villi and the small intestine, and they're combined with things like HDLs, cholesterol, right, LDLs, and then they're transported to your through the bloodstream to your adipose tissue, where they are again changed back into the triacylglycerols, right, and then are stored. It's a cycle. It's a cycle of making triacylglycerols and fats. So other cool things that can happen here is you can do saponification, right, where you react fat with strong bases such as sodium hydroxide, and you can make soap, right? So you take like the triacylglycerol that has palmitate or palmitic acid in it, right? Also known as tripalmitin or tripalmitate, right? Glycerol tripalmitate. You heat it up with some hydroxide, sodium hydroxide, right? And you'll end up getting the glycerol. But the cool thing you'll get though is sodium palmitate, the salt, right? The salt, not the fatty acid with the possibility of having a hydrogen there, right? But the salt version, right? Which is the palmitate, 3 sodium palmitates, right? And that is actually soap. Pretty cool. So this actually gives you like solid soap, like Irish Spring soap or Dove or something like that, right? Whereas if you use KOH, a slightly weaker base, right? I was about to say hydroxide, but they both have hydroxide. KOH is potassium hydroxide, which is slightly weaker than sodium hydroxide. That's how you get like softer liquid soaps, right? Softer liquid soap. Liquid soaps. Cool stuff. Cool stuff. So next I have a summary here of these lipid reactions that you should be well aware of, right? And you have an esterification reaction. That's a carboxylic acid plus an alcohol, right? With acid and heat, and you'll get ester and water. So what is an example of that? That is 3 fatty acids plus a glycerol. Makes a triacylglycerol and 3 waters, right? So that's when you form a triacylglycerol. Then in a hydrogenation reaction, we have a double bond alkene in the fatty acid, right? One of our unsaturated fats, with hydrogen and a metal catalyst. In this case, it says, in this case, it's a platinum, right? And you'll get a single bond. And the same thing can happen in fats. An unsaturated fat with double bonds plus some hydrogen gas in the presence of nickel catalyst gives you a saturated fat with single bonds, right? And then in hydrolysis, in a regular organic reaction, we have an ester plus a water, some acid and heat, and you get a carboxylic and an alcohol. A carboxylic acid and an alcohol, right? But you can also do that in lipid chemistry too. You get a triacylglycerol, which is a fat, right? The one that has the 3 fats connected with the glycerol. Add that to some water and some enzymes called lipases, and you get 3 fatty acids separately, and it's glycerol. And then saponification. Is the ester plus sodium hydroxide will give you a sodium salt of the carboxylic acid plus alcohol. If you recall that from the previous lecture, all right? Same thing can happen here with fats and fatty lipids. You have a triacylglycerol here, added to 3 sodium hydroxides, heat, and you get the sodium salt of the acid, fatty acid, which is a soap, and glycerol. Good stuff. Good stuff. So keep that chart in mind. Keep that chart in mind. And then last but not least for this particular talk, let's do some lipid reaction practice. Okay? So I have here now, right? This is, write the equation for the reaction catalyzed by an enzyme lipase, right? That will hydrolyze glycerol chlorate. Oh, by the way, if you didn't know this, laurate, right, is like lauric acid, which is when you use it to make soap, right, is the stuff that's in your uh, uh, shampoo, by the way, right? So if you look if you look in the on the back of the bottle of your shampoo, most of the time you'll see this molecule in there, and it's sodium lauryl sulfate, right? That's that, right? So it's taking a fat and it's saponifying it, lauric acid, right? And you get shampoo out of it. Just check the back of your. I challenge you again in this lecture to check the back of your shampoo bottle to see if you see anything there that is that is labeled in your instruction in your ingredients of your shampoo bottle, sodium lauryl sulfate, right? Because that's the sodium salt of lauric acid, the fat. Anyway, let's turn this into some soap, right? Some shampoo, using some enzymes. We'll start with this here. We have our glycerol right there, remember? And then we have our fatty acid part right here. All right, okay. Easy stuff. So let's start out by just drawing our glycerol. Right, there's my glycerol. Okay. And then lauryl, or lauric acid, has 12 carbons in it. Right? So let's draw out our. Why did I write a 10 there? That was so weird. There we go. Draw out our carboxylic acid there, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? Or you could draw it this way too. Remember the short way. Right? Right? 12 carbons. But I prefer the line angle way. It looks like more like chemistry. Oh darn it, I lost count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go. And that's how you answer that question. Okay? But however way you decide that you're going to answer this question, you make sure you pick one way or the other to answer the question. Either draw it in its condensed formula or draw it in its line angle formula. Okay? So, phospholipids are in a family of lipids, right? That are similar in structure to the triacylglycerols, right? But they include the glycerol phospholipids and the sphingomyelins, right? So here's your glycerol phospholipids right here. And they have a hydrophobic head group with a phosphate connecting to a glycerol backbone to two fatty acids right down here. Okay? The hydrophilic head group of a glycerol phospholipid has either a choline attached to it, an ethanolamine attached to it, a serine, and an isotal or glycerol attached to it, right? So that's where the glycerol phospholipid part comes from, right there, the glycerol, right? And then for the sphingomyelins, right, there's also a hydrophilic head group. The X there, or there, I use the word, I like to use R, but X there is a choline, and it's connected to a phosphate, right? They connected to the sphingosine backbone. That does include a fatty acid chain, right? And then another fatty acid, right? Another fatty acid. Excuse me. I think I just got an email. Let's mute that. There we go. So, just quick review. Glycerol phospholipids. Sorry, I got a little bit distracted by that. But from my email. Glycerol phospholipids contain two fatty acids that form an ester bond with the first and second hydroxyl groups of the glycerol. Right? Very similar to the triacylglycerols, right? Because in a triacylglycerol, you wouldn't have the phosphate group right here, right? You would just have another fatty acid coming down, right? from the glycerol. A hydroxyl group that forms the ester with the phosphoric acid, which forms another phosphodiester bond with an amino alcohol, right? Which is right here. So, oh, that's a new word right there. A new functional group. New functional group, a phosphodiester bond. Or a phosphodiester, right? That's something new. And what is a phosphodiester? It's when you have a phosphorus, like you see right there, connected to an O, connected to an R, right? Phosphodiester. And usually it's connected on both sides. That's why it's called a diester. That's a let me just draw that one more time. It's called a diester because it's usually like this. There we go. Right. So in the case of the glycerol phospholipid right there, right? So we'll call that R1 and R2, right? Rest of the molecule 1, rest of the molecule 2, right? And in the case of the glycerol phospholipid, right? This part here of the phosphodiester bond is the R1, and then this part here, which with the hydrophilic head group, is R2. Right? And in between we have our phosphodiester bond with the P of the phosphodiester bond. Right? Now, if you're really good, you'll know where else we see a lot of phosphodiester bonds. And if you can tell me before the end of the lecture, I don't know how you're going to tell me. Maybe you can email me or something like that. Right? I just thought that might be very unfair, though, because some people might watch the lecture before other people, and then they won't get a chance at this particular reward. So I'll just go ahead and tell you. Phosphodiester bonds are actually very prevalent in DNA because your DNA is made of a phosphodiester backbone, right? Interlinked with sugars, actually, riboses. But we'll talk a lot about those phosphodiester bonds and those riboses when we get to the DNA part of our class. Then we have our sphingosines that are attached to glycerols instead of, let me say that again. Our fatty acids are attached to sphingosines instead of glycerols in sphingomyelin, right? Like we were talking about here. And it contains one fatty acid, a phosphate, and an amino alcohol, right? Interesting stuff. So what are these hydrophilic head groups that are present in glycerol phospholipids? The ones that I mark as X in the previous slide, right? What are some of those? That's a terrible looking X. Let me try that again. There we go. And that was the hydrophilic head groups. Of the glycerol phospholipids, right? What were some of those? Well, there's choline and there's irine, which is not real because that's a typo. That should be serine. That's an amino acid, right? Not irine. And then we have ethanolamine, right? That's some of them. And they are actually considered hydrophilic because at physiological pH of 7.4, they're ionized, which means they're charged, right? So looking at choline here, we have a charged nitrogen. And looking at serine here, we have another charged nitrogen. And looking at ethanolamine, we have another charged nitrogen. And that's why they're considered, or they're called, the hydrophilic head groups, right? Or X in my previous picture. So let's see them in actual glycerol phospholipids, right? One of those glycerol phospholipids is lecithin. Lecithin has a choline head group that's polar, right? It's got its phosphodiester bond right there, connected to its glycerol right there, and the nonpolar fatty acids are there. And this is a 1 plus 14 is 15, plus one more is 16. That's a palmitic acid. Or palmitate. Right? Another glycerol phospholipid is cephalin, right? Cephalin means head, so I'm guessing that's in the brain. Its hydrophilic head group, or X, is ethanolamine, connected to its phospholipid. Its phosphoester bond, and its glycerol, and it also has palmitate as its nonpolar fatty acid tails. Right? So let's take a closer look at the structure here of glycerol phospholipids. Right? Remember that glycerol phospholipids always have a polar head group. So in that case, it's a choline. So that's lecithin. It has the phosphodiester, but before it joins, it's actually just a phosphoric acid. It has the glycerol, and it has the fatty acid tails. And this is actually a mixed fatty acid because it has a kink right there, right? So we have a saturated fatty acid up here, and we have an unsaturated fatty acid there, right? So largely, though, we consider that phospholipids are composed of two parts. The polar head, polar because the phosphate here is negatively charged, and the choline here is positively charged. And then we have the nonpolar fatty acid tails. Right? Fatty acid tails. That's what that little drawing is there. So it even has little nonpolar tails for you right there. And there's some implications there because since this is nonpolar, the fatty acids are nonpolar, these are what we call, or what we consider, hydrophobic. Right? And since these are polar, they're definitely soluble in water, we consider these hydrophilic. Alright? So hydrophilic, polar head group, soluble in water. Hydrophobic, nonpolar tails, not soluble in water. And so these have interesting implications. I was about to write out the word interesting, but I don't know why you would need me to write that out. Interesting implications when it comes to the cell membranes of your body, your cell membranes, right? And here are those implications. No, I'm just kidding. This is just, it's related, right? So snake venom, turns out, right, is actually composed of phospholipid lipases, right? And if you recall from a previous slide, I was talking about how lipases, or maybe it was a previous lecture, I was talking about how lipases in your digestive system break down the triacylglycerols that you consume, and they break them down into their substituent fatty acids so that they can be transported throughout your body to your adipose tissue for storage, right, in the bloodstream. Well, snake venom has phospholipid lipases. So what do you think those do? They break down the phospholipids that compose the cell membranes of your red blood cells, which is bad because that will destroy your red blood cells. You won't be able to transport oxygen anymore, transport nutrients to the rest of your body anymore. That's a bad thing. So getting bitten by a snake and being poisoned with snake venom is a bad idea. But of course, we have antivenom, which counteract those effects, right? Counteract those effects. But that is how snake venom works. It hydrolyzes the phospholipids in the cell membranes of your red blood cell. So another group of phospholipids are the sphingomyelins. Sphingomyelins. It's hard words to say. Anyway, and you can see in the structure of these sphingomyelins, they're very similar to the glycerol phospholipids. except that you have this thing that is the sphingosine backbone, right? And the sphingosine backbone is this part right here. Right? Oh, sorry, missed this carbon right here. So that's a sphingosine backbone, right? And if you notice, it's a little different from a glycerol phospholipid, because in the glycerol phospholipid, this was an oxygen, right? And in addition to having the hydroxyl there, there's also this long chain alkene on the sphingosine backbone, right? So sphingomyelin is composed of the sphingosine backbone, and then the fatty acid, here in this case it's palmitic acid again, 16 carbons long. The phosphodiester bond right there. I just spelled phospho with an F. That's terrible. There we go. Phosphodiester. Alright. And then we have the choline. Hydrophilic head group. Right? So these guys are abundant in the white matter of your myelin sheath surrounding the nerve cells, and it increases the speed of nerve impulses, insulates and protects nerve cells. Right? So that's where sphingomyelin is. Then we have our steroids, right? Steroids usually consist of 3 cyclohexane rings and 1 cyclopentane ring fused together. These rings are designated A, B, C, and D, as you can see here. A, B, C, and D, right? And the reason why it's called a steroid nucleus is because all steroids have this part, and then they just have other things coming off of them as substituents and such, right? We always number the carbons beginning with carbons in ring A, right? And then the 2 methyl groups are always at position 18 and 19 for the steroid numbering system. Not much else there to say about steroids, except for the fact that cholesterol is a steroid, right? And you notice here that it has the A, B, C, and D rings, and it has hydroxyl substituents here and this alkane substituent there off the D ring, right? So cholesterol is the most important and abundant steroid in the body, and it has a hydroxyl group at carbon 3. It has a double bond between, oh, I forgot to mention that, it does have a double bond between carbons 5 and 6. The 2 methyl groups are there like they were in the steroid nucleus in the previous slide. And then the alkyl chain that's connected to carbon 17, right? So they are present in meat, milk, and eggs. They're synthesized in the liver, and it is needed in cell membranes, brain, and nerve tissue, and steroid hormones, and vitamin D. But it also clogs arteries when there are high levels of plaque form, right? So here we have a nice clean open artery, and here we have an artery clogged by cholesterol plaque. You definitely don't want that. A little more about cholesterol here. It is considered elevated if the plasma cholesterol exceeds 200 milligrams per deciliter, right? It's synthesized in the liver and is obtained by foods. So let's take a look here. Beef liver has, 370 milligrams of cholesterol in every serving size. Good thing I don't like beef liver, right? I do like eggs though. One egg has 200 milligrams of cholesterol. Lobster less. Fried chicken. Oh my gosh, I didn't realize fried chicken had less cholesterol than meat and eggs. A hamburger even has less. Chicken with no skin and fish, salmon, they're all very low in cholesterol, right? Skim milk only has 5. Margarine has no cholesterol, but butter has cholesterol in it, right? Because it's the milk and the butter. Margarine is mostly made of oil, if you recall, right? So what are biosalts then? It turns out those are cholesterols too, right? So here's the structure of a biosalt, specifically sodium glycocholate, right? And it consists of a cholic acid here, right, attached to the amino acid glycine here. It's sodium glycocholate because of the sodium that's there. So this is the sodium salt of the amino acid glycine, right? They're synthesized in the liver from cholesterol, and what they do is that they make fat more soluble in water, so it helps with the absorption, right? It helps with the absorption. But the problem though is that if there's too much cholesterol in the gallbladder, gallstones are formed, and I hear that's not very pleasant, right? But so a lot of people have to remove their gallbladders, and when they remove their gallbladders, they don't do they're not able to actually process and absorb fat as easily because of the lack of the biosalts that assist in the making that act like soaps to assist in making the fats more soluble in water, right? So I had a professor once that used to love having butter dipping sauce with her lobster, and she had her gallbladder removed, and it was not a good time for her when she forgot that she couldn't eat that that butter with that lobster. All right, let's talk about lipoproteins in more detail. If you remember what I was talking about when I spoke about it before, lipoproteins are what your body uses to transport the substituent fatty acids from your triacylglycerols that are broken down by your digestive system, right, through the bloodstream. Well, how does it do it? Well, consider this is the fatty acid that was broken down from the triacylglycerol that you consumed, right? And it was broken down by lipases in your stomach and your small intestine by the lipases into its substituent fatty acids, and it's attached to then a cholesterol, right? So this entire thing is called a cholesterol ester. These cholesterol esters are all combined with each other, right, inside of it's almost like a cell membrane, except it's not a bilayer, it's just a single layer, right, of phospholipids, right? And so what happens is that when all these cholesterol esters are surrounded by a phospholipid layer, right, that also has some cholesterols interlaced in between, it makes them more soluble in water so that they can be transported through the bloodstream, right? And so that's essentially what a lipoprotein is, right? That's essentially what a lipoprotein is. A lipoprotein is basically membrane proteins and phospholipids and cholesterol assembled in a single layer membrane, right, to basically make a ball, capturing inside the ball the broken down triacylglycerol that's been attached to a cholesterol for transport through the bloodstream, right? Because it makes it more soluble in water. Not all of it is broken down triacylglycerols that are broken down into fatty acids. There are also some whole ones too, right? Whole triacylglycerols. But the point of a lipoprotein is to surround a molecule, like a fatty acid molecule. They make it more soluble in water so that it can be transported through membranes and the bloodstream to either cells for usage as energy or for to be used to be stored, right? So let's talk about the different types of lipoproteins. There are the chylomicrons, the high density lipoproteins, low density lipoproteins, and the very low density lipoproteins, right? And by density, we mean that by number too, right? We mean that by its actual density. High density lipoprotein on one end of the spectrum is 1.06 to 1.21 grams per milliliter, whereas a chylomicron, or even a very low density lipoprotein, it goes as low as less than 1 gram per milliliter, right? Why is that? Well, let's take a look at its composition by mass. The chylomicrons are mostly composed of unbroken down triacylglycerols, right? And the rest of it is the phospholipids that compose the membrane, the cholesterols in the membrane, the cholesterol esters and the cholesterol esters inside, and the proteins in the membrane, right? So chylomicrons are basically all triacylglycerols that haven't been broken down by your lipases into their substituent fatty acids. Very low density and low density lipoproteins, right? Again, very low density lipoproteins, very high percentage of triacylglycerols, right? Only 8% phospholipids, cholesterol, and protein. Those are the things that compose the membrane, right? And then 12% cholesterol esters. That's the broken down fatty acids from triacylglycerols that have been attached to a cholesterol molecule. Looking at regular low density lipoproteins, this is not mostly triacylglycerols, right? This is what these are what really transport your fatty acids that have been broken down from what you've eaten, right? And that's why it's mostly these cholesterol esters, right? And then 22% membrane, phospholipids, cholesterol membrane, and 22% protein. Now, what makes HDL so good as compared to LDL? Turns out that it's mostly protein, right? 55% of a high density lipoprotein is protein, and then 24% is phospholipids. So the vast majority of this stuff is like membrane, right? And only 15% cholesterol esters, so very low fat, right? Very low cholesterol, and very low triacylglycerols, right? And that's why they say health practitioners and dietitians and nutritionists all say that it's good for you to have a lot of HDL and very little LDL, right? Because LDL is mostly the fats that you eat that come from those triacylglycerols, right? And there's very little of that in HDL, right? High density because, and you might be asking yourself, "What? I don't understand what this is here," because it says high density and there's not as much fat. Well, actually, it's high density because it's more protein, right? And protein weighs more than fat, and that's why it's higher density than low density lipoprotein, which has less protein and more fat, right? That's why people always say, when you're working out and you're building muscle, you never lose any weight, and that's because muscle weighs more than fat does. Well, the same is true in lipoproteins as well, right? So shoot for those high density lipoproteins; they're good for you. So, let's say you're eating a piece of bacon. That kind of looks like bacon. And it goes down in your stomach. And the bacon fat in the form of triacylglycerols are broken down into their substituent fatty acids, and those fatty acids are attached to cholesterols, and those cholesterols are grounded up into LDLs, right? And they go straight to your heart and start clogging up your coronary arteries, right? Bad idea. Bad idea. Get some more HDLs in there, right? Get some more HDLs in there. But generally, though, lipoproteins such as HDLs and LDLs transport nonpolar lipids and cholesterol to cells in the liver for either energy storage, right, or fat storage, or usage, right? So let's quickly go through some hormones, some steroid hormones. Sorry, let me say that again. Let's quickly go through some steroids, right? The first steroids we're going to go through are the hormones, the steroid hormones. We have testosterone here, estrogen here, progesterone here, and norethindrone here. Excuse me, right? And we all know that testosterone, progesterone, and estrogen, right, are sex hormones. And then we can see here that they look just like steroids because they have the A, B, C, and D rings. It's interesting though because estrogen has a aromatic ring in the A ring, right? But all these other ones have double bonds in the A ring, just single double bonds in the A ring, right? And other substituents making them different, right? So then we have the anabolic steroids, different from the hormone steroids, right? Or the steroid hormones. And these are actually all derivatives of testosterone, and they're illegally used to increase muscle mass, but they have bad side effects, like fluid retention, weird hair growth, sleep disturbance, and liver damage, right? But again, these are all just steroids, A, B, C, and D, right? They all have it. And these are particularly difficult to say. Methodienone, right? You see here back to our organic chemistry naming, one, right? Because it has a ketone right there, right? Then we have oxandrolone, which has an one there because it has a ketone right there, right? Then we have nandrolone and stanozolol, right? Still a steroid though. It has another 5-membered ring over here, but it's still a steroid because the steroid center is still there. Steroid nucleus, right? A, B, C, and D. Next we have the adrenocorticosteroids. These help regulate different systems in your body. For example, we have aldosterone, which regulates the electrolytes and keeps water balance by the kidneys, right? And then we have cortisone, or also known as glucocorticoid, right? And that actually increases blood glucose level, and stimulates the synthesis of glycogen in the liver. And if you don't remember what glycogen is the glucose storage molecule in your body, right? It turns glucose into glycogen when there's insulin. So here's cortisone, also steroid, A, B, C, D, right? Here's aldosterone, helping with those electrolytes. Cortisol, and one that you should all know, prednisone. How many times have you had to take prednisone because of allergies or something, like a bad allergic reaction or something? I mean, I've had to take a cortisone shot every once in a while because of my bad allergies. But these are the things that we use, right? Because they're actually immunosuppressants. Steroids, corticosteroids like cortisone and prednisone are immunosuppressants. And when you have allergies, that's actually an overreaction of the immune system, and that's why they give you corticosteroids, because they suppress the immune system. Next. Only a couple slides left, and we're going to now finally talk about the cell membrane. As you all probably know from biology class, right? Freshman biology class, our cell membranes consist of a phospholipid bilayer, right? So you can see here in this picture here, there's the hydrophilic head that's water soluble, that likes water, and then the hydrophobic tail, right? If you recall from a previous slide, right, this is what we usually see, and this is the hydrophilic head. Right, like a choline or something, or an ethylamine. And then these are the lipid tails that are hydrophobic. Hydrophobic. There we go. What does that mean? Well, these are nonpolar on this end, and these are polar on this end. Which means that it likes to be around water on this side, and it hates to be around water on this side, right? So naturally then, these phospholipids will arrange themselves so that their polar side, right, is facing towards the water, right, facing towards the water. But this is different from the lipoproteins, because the lipoprotein only had the single layer of the phospholipid, and then on the nonpolar side was those fatty acids, right, with the cholesterols, right? And so that was pretty nonpolar, and so it was fine being on the same side as the hydrophobic nonpolar tails, fatty acid tails. But for this to be a bilayer, the other side is another phospholipid flipped upside down, so that its nonpolar side, right, is over here. Sorry, its polar side is over here. Except that you can't see because my head is in the way, so let me change the view real quick. There we go. Its polar head is on this side, right? And now there are two sets of nonpolar tails right here, and they're facing each other. Why is that good? Well, that's good because now you can have water on both sides. Right? So inside the cell membrane is your cytoplasm over here, and your nucleus, and your all the different organelles that are essential for cell function. And then over here is the outside of the cell, where it's also water, right? And it can receive different nutrients and proteins and hormones and such like that, right? So that's what it means by a phospholipid bilayer. So what's really interesting about that, though, is that there's this thing called the fluid mosaic model of the cell membrane, and what it actually means is that everything that's positioned inside the cell membrane is very fluid. It's not static. It moves around throughout the membrane, right? And you can't see me because my picture is gone, but I'm moving my hands around very fluidly. Let me just switch back so you can see. There we go. Very fluidly. Everything in the cell membranes are moving around very fluidly, right? And that includes things like cholesterol, right? Receptor sites for hormones and transport proteins, right? And they're positioned in those cell membranes in such a way so that the parts of them that are afraid of water or hydrophobic, right, are anchored to the center of the cell membrane where it's also hydrophobic, and the parts that are hydrophilic are exposed to the water sides of the phospholipid membranes, right? So that it makes it easy for the cell to control what enters and leaves the cell through these proteins, right? Through these transport proteins. All right? So the thing you got to remember about the cell membrane, right, is that it is a phospholipid bilayer, right, where the polar heads of the phospholipids are exposed to the water side on one side of the cell membrane. Then on the other side of the head, right, are the lipid tails, fatty acid tails, and they butt up against more fatty acid tails and another polar head of another phospholipid, right? And just imagine all these just surrounding around little bubble of water to make a cell. And then outside the bubble of water is also of the membrane is also water, right? Where there's nutrients floating around and such, right? And so you can get nutrients from outside the cell, inside the cell, by having transport proteins or signal things, instruct the cell to do things using receptor proteins, right? Receptors and things like that, right? And then the organelles inside the cell are safe in the nice little hydrophilic area of the cell, right? That's all enclosed by the phospholipid bilayer, right? So it's much more complicated than that because there's an entire class that I took called cytology, and it's all about the cell chemistry and such. But you just have to remember how the cell membrane is composed, right? Once again, phospholipids, heads are exposed to the water slides that are hydrophilic. Tails are facing each other, right? That are hydrophobic. And then there are proteins and receptors and carbohydrates and all kinds of other things that are floating around very fluidly in that membrane, right? For cell function. So it contains proteins, carbohydrates, and cholesterol, which I already said that. Has unsaturated fatty acids that make the cell membrane fluid rather than rigid, right? And has proteins and carbohydrates on the surface that communicate with hormones and neurotransmitters. Yep. But that's all I really want you to know about the phospholipid tail. How is this different from the other one? Remember, I spoke about this just a second ago. These are very similar to high density, low density lipoproteins, except the high density lipoproteins and low density lipoproteins only single layer, right? So it can't be water on both sides. It's water on the outside and then hydrophobic on the inside, and that's where the fats stay and they get transported through your bloodstream that way, right? Just making sure you remember that. And then our very last slide, a little bit more detail about transport through cell membranes, right? There's diffusion, which is also known as passive transport. Particles move from a higher concentration to a lower concentration, and we've talked about this before with osmotic pressure, right? Being hypotonic, isotonic, or hypertonic to the surroundings, right? There's facilitated transport, which uses protein channels to increase the rate of diffusion. So that's how the cell gets different materials from outside the cell inside the cell that are specifically needed, and that's with the transport proteins. And then there's active transport, which moves ions against the concentration gradient, right? So just real quickly here with this picture, we have here diffusion, which is passive transport, and when the concentration inside the cell, right, is less than the concentration outside the cell, then diffusion will happen so that the concentration inside the cell becomes more like the concentration outside the cell, right? Because right now it's hypertonic outside the cell. And it wants to become isotonic, which is same on both sides. Now, if we're opposite and there was more on the inside of the cell, then it would go the other way, right? Because then you would be hypotonic outside the cell. Right? And then we have our facilitated transport right here. And that's done by a protein that has a special little channel, right, that goes between the two layers of the phospholipid bilayer, right? And it transports specific molecules into the cell. And then there's active transport, where it requires energy, right, to actually push things like waste outside the cells, right? And that is very cursory how transport through cell membranes work, right? All right.